This educational series has been written and prepared by the Service Department of the Electromotive Division of General Motors Corporation to outline specific airbox service examinations and procedures. The objective of this airbox inspection series is to illustrate the tasks necessary to properly perform an airbox inspection, component qualification during an airbox inspection, and the reasons an airbox inspection should be part of a regular maintenance program. Here's a safety note. It's most important to take all possible safety precautions prior to inspection to ensure that the engine cannot be accidentally started while service procedures are being conducted. On a locomotive, remove the start fuse before performing an airbox inspection. We'll be using the following easily obtainable tools during our airbox inspection: a flashlight, a feeler gauge, lead wire, a cylinder test valve wrench, a ratchet with 5/8" socket, and your engine service manual. Our initial service procedure is to determine the engine's overall condition. Note carefully if this is a routine airbox inspection or if it is the result of a mechanical failure. In either case, thorough attention to detail is required. Remember, if the engine experienced a crankcase shutdown, you must wait a minimum of 2 hours before opening the top deck covers or any handhold covers. Opening these covers prematurely adds oxygen to the unburned fuels and vapors that already exist inside the crankcase, possibly resulting in a crankcase explosion. On this engine, we're going to perform a routine airbox inspection. First, remove the airbox handhold covers. Using a flashlight, visually check for carbon deposits, port restrictions, and water leaks. Water leaks left unattended may result in power assembly failure, oil contamination, and turbocharger exhaust inlet screen and nozzle ring blockage. Heavy deposits of oil-soaked carbon and sludge in the airbox can cause an airbox fire, resulting in component failure and turbocharger overheat overspeed. Restricted air inlet ports reduce the amount of air available for combustion, resulting in a substantial loss of power and possible power assembly damage. Heavy carbon deposits and port restrictions are caused by continued service with one or more of the following component or system malfunctions. A careful inspection may uncover bad fuel injectors or improperly adjusted injection timing. The fuel rack may be improperly adjusted. Look for broken top piston rings or scored and worn cylinder assemblies. Both are possible contributors to heavy carbon buildup. Additionally, an airbox full of carbon and sludge can be caused by any of the following: plugged engine air filters, plugged inertial filters, plugged aftercoolers, or a severe turbocharger discharge air leak, governor malfunction, or electrical overloading. The next step in our airbox inspection series calls for a thorough check to determine piston ring condition, plus a check of the side clearance on the number 1 compression ring. Refer to your engine service manual for detailed inspection data. Open the test valves, then bar the engine over until the flywheel reads 0 degrees on a turbocharged engine, 356 degrees on a Roots blown engine. Using the 1 revolution inspection sequence chart found in your engine service manual, we can determine which cylinder can be inspected through the liner air ports. This engine is a 16-cylinder turbocharged engine. So, at 0 degrees on the flywheel, we can see that cylinder number 6 is on the way up, and the number 1 compression ring is accessible through the liner air ports. Use a feeler gauge to check the side clearance on the number 1 compression ring. Due to the normal compression ignition cycle, the side clearance will increase and eventually enter a breakable stage. We can use the number 1 compression ring's side clearance as a guideline to try and replace power assemblies before ring breakage does actually occur. The side clearance on this number 1 compression ring is so excessive that the gap is blatantly visible between the bottom of the ring and the ring land. Use an ordinary wooden stick to check for resiliency on the compression rings. Push on the rings. They should spring right back. If they don't, they're either broken or restricted by a heavy carbon buildup. We'll classify the condition of the compression rings according to data found on the ring wear classification chart in your engine service manual. Examine the grooves in the compression rings. They are wear indicators. They help you gauge the amount of useful life left in the rings and tell you when component replacement is actually necessary. Notice the chrome chipping off of this compression ring. Chrome chipping off of a compression ring should not in itself be a basis for power assembly replacement. Our next task on cylinder number 6 is to illustrate a lead wire reading. A lead wire reading may be used during an airbox inspection to indicate wear trends. Significant clearance increases over initial installation readings should be investigated as possible component failures. Using a piston of the same size as the piston you're checking, position a piece of 1/8-inch lead wire over the top of the piston so that the lead wire accurately conforms to the shape of the piston. The wire should then be cut away exactly 1/8 inch from the outside edge of the piston. Then, install the lead wire through a liner port, parallel to the crankshaft. Bar the engine over 1 complete revolution to compress the lead wire. This compressed wire can then be measured to indicate the amount of power assembly wear. Remove the lead wire and use a 1-inch micrometer to measure both lead wire ends. On a new engine, allowable clearances range from a minimum of 20 thousandths of an inch to a maximum of 68 thousandths of an inch. Lead wire readings must not vary more than 5 thousandths of an inch from side to side. If greater differences in readings do occur, take a second lead wire reading. If the second lead wire reading still shows a difference from side to side of greater than 5 thousandths of an inch, the power assembly must be replaced. Now, for a review. What problems can port clogging and heavy carbon formations cause? Poor engine combustion, possibly leading to an airbox fire and eventual damage to engine components. What are some of the most common causes of heavy carbon deposits in an airbox? Here we have a long list of probables, any one of which can be the answer in your particular inspection. Bad fuel injectors or improperly adjusted injection timing. Injector rack out of adjustment. Broken compression rings. Cylinder scoring. Plugged inertial filters. Plugged engine air filter. A severe turbocharger discharge air leak. Governor malfunction. Electrical overloading. What task can prevent ring breakage? Use a feeler gauge to check the side clearance on the number 1 compression ring. Why are lead wire readings taken during an airbox inspection? To indicate wear trends only. Lead wire readings should not be used as criteria for power assembly replacement. That's the end of Section 1 of our service procedures. Discuss Section 1 with your instructor. Let's move into a more thorough study of airbox inspections. Refer again to the 1 revolution inspection sequence chart found in the rear of your engine service manual. Let's inspect the piston condition on cylinders number 7 and number 16, and the liner condition on cylinder number 4. Look through the cylinder liner air ports to inspect the piston surface. For additional data, we'll refer to the piston liner visual inspection guide found in the rear of your engine service manual. We'll be inspecting the piston for the following signs of wear and malfunction. Scuffing or scoring. If the scuffed area on the piston is larger than 3 by 4 inches, replace the power assembly. Carbon deposits. Check the piston for signs of severe carbon deposits. They indicate poor or incomplete combustion. While you're looking through the liner air ports, you have an opportunity to inspect the liner itself. Again, refer to your engine service manual for additional data while we inspect for any of the following liner problems. Cylinder liner scuffing will certainly involve similar scuffing of the piston. Again, inspect the piston. If a scuffed or scored area larger than 3 by 4 inches is found, replace the power assembly. Look for port streaking and port milling. They're vertical marks starting at the port edges. These marks, however, usually do not affect hone marks in the liner bore. Streaking and milling do not require power assembly replacement. The cylinder liner and piston may continue in service, but caution is called for and further close inspection should be performed at periodic service intervals. Carbon drag and port framing are common cylinder liner problems. Carbon drag is a highly polished area in the liner bore that may appear black, blue, brown, or tan in color. Hone marks are usually not visible. Port framing refers to the squaring off of normally rounded port corners. Ports normally look like a square with rounded corners. Varnish appears in the cylinder liner when the engine is continuously underworked. Periods of light loading, extensive idling, and improper lube oil viscosity. Use the 1 revolution inspection sequence chart to complete your airbox inspection. Carefully check all pistons and liners for the malfunctions and problems we've just outlined. Scuffing, scoring, carbon deposits, port streaking, port milling, carbon drag, port framing, and varnish. Now, for a review of Section 2 of our airbox inspection series. How much scuffing can be allowed before a piston must be replaced? An area of no more than 3 by 4 inches. Any more scuffing than that, and the power assembly must be replaced. What causes a liner to varnish? Light loading, extensive periods of idle, and improper lube oil viscosity. A properly detailed and thorough airbox inspection can help to anticipate and prevent needless component replacement, serious engine failure, and costly downtime.